Alright, this is my video recording for homework 2 for CS262, the parser combinators. So first of all, a parser is the step in the pipeline that comes after the lexer, in the compilation pipeline that comes after the lexer, turning the series of tokens, which, you see we're getting out of this pre-created lexer, into more organized syntax, a syntax tree, which can then be traversed to actually execute code and do things. I implemented this using the nom parser, which is a Rust library that enables us to make better parser combinator functions. And I used, as you can see, a few of their helpful combinators, such as many1, many0, and tuple, which in this case all helps to do stuff that was helpful to abstract away, so I could focus more on the business logic. I have a variety of these low-level items just to turn a token, to parse a token, where they just check using this check token function, which is in the lexer. It is also a parser combinator, but it outputs a token as well instead of a node in the tree. The way these all work is that if they see that what they saw is the thing that they are parsing for, then they go forward and return both the part that was just parsed and the rest of the string to be parsed. And if they don't find it, they just return nothing, because it's all recursive. You can have any number of these functions checking. So check token will, very similar to what we had in the lexer, look at the token again and again until it finds one that, and if it finds one that is of the specified type, these functions will return true. And I also have some helper functions that were pre-written, just seeing many1, which is equivalent to these curly brackets where it's 1 or more, many0 is 0 or more. That's from the nom library. I had similar token returning parser combinator functions for multi-character tokens, such as return. Then we're getting into the real stuff here. These parser combinators return a node on the syntax tree. This one was pre-written, so I'm going to start with numbers, which can be any number of digits. So 1 or more digits, 1 or more of this token digit type. It keeps looking until it finds something that's not a digit. And if it found 1 or more digits, then this function was a success. And it keeps going down that syntax tree. Some interesting choices I had to make here. Just going down the list of functions. For Boolean, getting the value of the Boolean, did an if-else expression on the kind of the tuple that's returned from the Boolean raw parser combinator that takes a token. For string, I could have done the delimited kind of parser combinators that take and discard something, but I decided to keep it simple and just use another low-level single character getting parser combinator that just took a quote and then we just don't use it. It's just an underscore. For a function call, we get 0 or more function arguments. So the children of the item is a name, and they're either 0 arguments, in which case children is a empty vector, or some number of arguments, in which case we unwrap what we got from the arguments parser combinator, which is coming up. So I just like the design of this little match statement, where in the special case of the option that is args, the optional statement with this opt nom, very useful little tool there. It can either be none, or if it's not none, then it's something. But none is the special case here. A value which is not included in the available nodes because it's just either a number identifier or a Boolean. So this is very simple looking, just returns directly out of one of these nom parser combinators, in this case alt. Math expression looks for a value and then any number of pluses and minuses and one more value using many-one and tuple. To filter out the commas, again, I could have used delimited or one of those other parser combinators that look at and ignore something, except that I wanted to keep the value of the plus or minus because the name field of the math expression is add or subtract. So in this case, I made the most recent operation, like the last operation in the chain. If you have like 5 plus 2 minus 7, it's going to be minus rather than plus. I used this iterator stuff using a map with a little lambda of over each value of this result. An expression is pretty self-explanatory. It's just any of these. A statement is either of these followed by a semicolon. A set of function statements, which I was surprised was a node in the parser tree because I don't think it's in the EBNF, and it definitely wasn't in the comments describing when function statements had to be in there, but I just put it right after statement, so it's just one or more statements. Return, pretty self-explanatory. It's just return some value or expression. Defining a variable, pretty self-explanatory. Arguments, this is arguments to a function call. So similar to the math expression, I used an iterator to get all the values, except here we don't really care about the comma. Or that is a comma. I pasted that from the math expression one. So yeah, we're using a lambda, discarding the comma, and adding the value into a new vector. Function definition is the most complicated thing here. So we can have any number of arguments, including 0 arguments, so it's opt arguments. That's similar to function call, because it's supposed to be creating a signature. And function statements is abstracted away into this function statements thing, where it's one or more statements. And the name of function define is defined as the value of this identifier, which is the name after the function keyword. I decided to clone it and do this stuff to define it. Not necessarily the cleanest design, but it works. And that a program is just one or more function definitions. If I was going to extend this parser, I think first on the line would be just a bit more math operations. I mean, the lexer, I believe, finds, slashes, or I guess not asterisks, but I would add asterisks to the lexer, so we could do adding, subtraction, multiplication, division, modulo, and I would maybe change math expression, the way math expression works, to make this a little clearer about all the add and subtract and other expressions when there's a series of different values that are being combined together. Yeah, that's pretty much it. So let me go through my custom tests. You can add false and false. I'm kind of imagining this is like in JavaScript, where false equals 0, or even like in Lisp, like false equals 0 equals the empty set. You can add together multi-digit numbers and subtract 2, so the name of the math expression becomes subtract. You can have numbers, uppercase, lowercase letters, and identifier, adding together multiple numbers, and then identifier 2. Can have a function definition with exactly one argument. Can have a function definition with a function call in one of the statements, because it's just an expression. One of the options for an expression is a function call, and that goes within a defining of a variable with let. So perfectly legal. Can parse a full program, which is just one or more of these function definitions, and you can parse a full program with multiple function definitions. Let me show you all these tests passing. I'll ignore that. Right, so all these tests pass. So you can get a pretty good idea of what the syntax returned from the parser is just by looking at this. You know, a series of nested items, all of these within the final set of curly brackets. And let me run cargo run to show you the contrast between the unparsed text that comes out of the lexer and the parse tree. Here it's just an identifier, but you can pretty clearly see that there's more stuff coming out. And here's what comes directly out of the parser. This is correct because the top level thing is an identifier. It looks for an identifier. Let me modify main. Playing a risky game doing this live on video, but let me modify main to, I'm not going to do anything complicated, but just pasting from one of these tests. Alright, so you can see it parses everything. There's a function call with children of function arguments that, so the function call has the name foo, and it takes just a single identifier with name a. So foo, function arguments of a, and that's also what happens in the tests. So that is the output of the parser. I think that's it. Thank you.